Alright, what's up guys? This video is mainly for people who are absent today, but it'll help everyone. So it's Friday, it's 3:30 right now, so while you guys are having fun, I'm making this video for you guys, which is fun, I guess. So if you were absent on Wednesday, you missed this PowerPoint called The Mole. So please go over this. You don't need to do the song. But the point of this PowerPoint was to basically tell you what a mole is. Okay, it's just a number, this big number, the reasoning behind how we came up with this number, and just go through these slides. Like any mole of anything, a mole of anything is 6.022 times 10 to the 23rd of that thing. Okay, we did a song. We figured out what molar mass was, right? Molar mass, the mass of anything in one mole of the mass of 1 mole of anything. So if you figured out the molar mass for sulfur trioxide, you guys can figure this out easily, okay? And we did one more over here. And then we started off with percent composition. Percent composition is that's the percentage by mass of any element that we're targeting over the total molar mass of that compound, whatever it is. So we did an example problem at the end of the period on Wednesday for finding the mass, the percent mass of carbon in ethanol. So C2H5OH. What's the percent composition of carbon? So it's really simple. All you needed to do was take how many moles of carbon are in C2H5OH? What is 2 moles of carbon? So we just do 2 times the molar mass, which is 24.02 grams per mole. And then we divided it by the total mass, molar mass of ethanol, which is 46.08 times 100%. Keep the sig figs consistent at 4. And you had 52.13. And what we did today in class was we did just a slightly different problem where now I'm telling you that I have a certain amount of this compound, so 300.0 grams per 300 grams of calcium chloride. So if I just had a tube of calcium chloride or a tub of calcium chloride, I would just scoop up 300.0 grams. How many grams of calcium and chlorine would you have? So now I'm not asking for percentages. I'm actually asking for what's the actual physical gram value, what's the mass of each individual element in calcium chloride. So first of all, we need to figure out what the percentages are of calcium and chlorine individually in order for us to determine how much the actual gram value is. So it's like saying if you had 100 grams of Chipotle and you're sharing with your best friend, but your best friend wants to eat a lot, has an appetite, and wants 95% of that Chipotle burrito. Let's just say it's 100 grams. It's definitely more than 100 grams. But if the burrito was 100 grams, then your friend would effectively eat 95 grams of it, and you'd be left with 5 grams. So similar to this, we're given the total size or the mass of calcium chloride, but we don't have the percentages of calcium and chlorine. So we first have to figure out what the percent composition of calcium is by dividing the molar mass of calcium over the molar mass of calcium chloride times 100%. You get this nice looking percentage, 36.11. Those are my favorite numbers. And if you were to find the mass of chlorine or the percent composition of chlorine, you can either just subtract 36.11 from 100, because percents add up to 100 per cent. Cent means 100. Or you could just figure out the molar mass for calcium or for chlorine, times it by 2 because there's 2 moles, and then divide it by the total and get the same answer. Okay. Once you have this though, you have the percentages now, so you can simply just multiply the original total by whatever you have, so by the percentages, so in decimal form. So 0.3611 times 300, the original, will give you 108.3 grams of calcium, and then 0.6389 times 300.0 grams would give you 191.7 grams of chlorine. Okay, so there's 2 practice problems that ask you to find the percentage, so the percent composition, and then we did this one in class. Okay, that asks you to figure out the grams. This one we didn't do, so I'll just walk you through this. So if you decompose the 1.0 kilograms, which If you guys remember from metrics, 1,000 grams is in 1 kilogram. So this is the same thing as saying 1,000 grams, okay, of calcium, of carbon tetrachloride. How many grams of carbon and chlorine would you have? First of all, one thing, 1.0 kilograms is 2 sig figs. So if you were to say, if you were to convert to grams, you would have to keep that sig fig. So this is actually the gram value, 1.0 times 10 to the third power grams. Okay, 1.0 times 10 to the third is 1,000, but it's 1,000 with 2 sig figs. Because if you think about it, you can't ever make 1,000 just without scientific notation. You can't make 1,000 into more than 1 sig fig. Okay, 1,000 will always be 1 sig fig. If you put 1,000.0, all of a sudden that becomes 5 sig figs. So the only way to have 1,000 as 2 sig figs is to write it in scientific notation. So 1.0 times 10 to the third grams. But I'm getting ahead of myself. So same thing, you have to figure out the percentages for each element, so carbon and chlorine. So the molar mass of carbon tetrachloride is 153.82 grams per mole. You find the molar mass of 1 mole of carbon divided by 153.82 grams per mole, and you get 7.808%. Okay, and then for chlorine, you get 4 moles of chlorine, so 4 times the molar mass of chlorine, and then divided by 153.82 grams per mole, and you get 92.19%. Take the percentages, times it by what we have, which is 1.0 times 10 to the third grams. Okay, and you have 78 grams. And then same thing for chlorine, you multiply the percentage in decimal form times what we have originally, which is 1.0 times 10 to the third grams, you get 920 grams. Okay, 2 sig figs because of this guy over here. 2 sig figs, 2 sig figs, 2 sig figs. And you might be wondering, why do you have to do this in grams? Why can't you just keep it at kilograms? Because the question asks you how many grams. Okay, so that's it for today. Today's stuff. But the homework assignment you're gonna get had to do with this stuff over here. We also did this today, mole conversions. So we know that moles are really important because it's the bridge, it's the gap to happiness, right? It helps us to convert things and do a lot of other cool things. Okay, it's a pass-through unit, and here are the conversion factors. And it's 2 of this we already know. The one of it's new. Well, one we already know is that 1 mole is equal to 6.022 times 10 to the 23rd particles. If you have 6.02, that's fine. You can also use 6.022. It really doesn't matter. You're going to get the same answer regardless. I'm going to skip this middle guy for a second. We also know the molar mass. Molar mass is grams per mole. So 1 mole is equal to the molar mass in grams. That's just a molar mass as a conversion factor. The new conversion factor here is that for every 1 mole of a gas, okay, gases only, because gases are less dense than solids and liquids, 1 mole of a gas takes up 22.4 liters. So this is the volume value now. Okay, it says applies only to gases at STP conditions. STP means standard temperature and pressure. And the standard temperature is 0 degrees in chemistry, and the standard pressure is 1 atm of pressure. We use standard pressure and temperature because if the temperature or pressure changes dramatically, your reactions aren't going to happen the way it normally would happen under standard conditions. Okay, we know that heat can make particles move a lot faster. Changing the pressure can also have an effect on kinetic energy. There's a lot of variables that change. So to keep it consistent, we can't just say, well, this reaction can only happen in the North Pole. This reaction can only happen in Irvine. This reaction can only happen in Mr. Kim's mansion, right? You can't say that. I don't have a mansion. You can't say stuff like that. So instead, we just have a standard value that we just refer to, or all chemists do, which is STP, 0 degrees and 1 atmosphere. These actual values aren't that important right now. Later on, it will be important. So just keep this in mind. So everyone received a mole roadmap, which is right here. I already uploaded this on Haiku, so you can download it, print it out. But this pretty much, I'll just go back to this one. This pretty much shows you how the importance of the mole, where if you want to, let's say, convert from mass to number of particles or something, then you have to actually pass through the moles. So you have to first convert to moles, then go to number of particles. If you want to, let's say, go to particles to volume, you have to first convert to moles and then volume. If you want to go to volume to moles, then that's just one step, that's fine. Moles to volume, one step, moles to mass, one step. But if you ever want to go from like here to here, it's two steps because you have to always convert to moles first. Okay, so the goal in dimensional analysis, we are doing dimensional analysis, is to cross cancel. So as long as your units cancel out and you're left with the unit you want, then you're good. Okay, so we did this example in class. It's very basic. How many moles is 5.69 grams of sodium hydroxide? Well, the first step in dimensional analysis problems is to write the given. So here's the given, okay? And now we have to identify what we want. So that's moles. So that's easy. First of all, if you didn't know how to do this, all you need to do is first of all put grams over here because we have to get rid of this grams no matter what. And then just put the thing you want, which is moles right here. And you can't just automatically put what you want on the top. You have to make sure there is a conversion factor that exists. But we know that moles to mass is related through molar mass. So if we take the molar mass of sodium hydroxide, which is 40.00 grams, we can put the grams on the bottom and then 1 mole on the top, because for every 1 mole of sodium hydroxide, it's 40.00 grams. So just put that there. Multiply it out and you get 0.142 moles of sodium hydroxide. MOL is an abbreviation for mole. It's not an abbreviation for molecule. And it's 3 sig figs because of this guy. We don't count conversion factors as part of our significant figures. So we had a set of practice problems that we did. You can do this on your own. I'm actually going to do this one. Okay, we didn't go over this in class. So practice set number 2. What would be the volume of 0.12 moles of fluorine gas at STP? Okay, what would be the volume of 0.12 moles of fluorine gas at STP? I'll go back to these later, but let's first figure this out. Well, I wonder, oh yeah, I forgot I had this. Okay. If I do, I don't think the screen will, yeah, I'm not going to do animations. Yeah, it's not going to work. Yeah. Okay, so what would be the volume of 0.12 moles of fluorine gas at STP? Well, the given is 0.12 moles of fluorine gas. Okay. What we want is volume. So we're going from moles to volume. If you take a look at the chart over here, moles to volume is one step. It's the conversion factor utilizes the 22.4 liters for every 1 mole. So you just start with 0.12 moles of fluorine gas. Whoops, it's actually F2. Fluorine gas. I should put the G2 just to be consistent. Fluorine is a diatomic, so this is why it's F2. Okay, to go from moles to liters to volume, that's easy. Because we know that for every 1 mole of a gas at STP, and it says at STP, it occupies 22.4 liters. So we just simply put this over 22.4 liters. Moles cancels out, and we're left with 2.7 liters of fluorine. 2 sig figs, 2 sig figs. Okay, make sure to write the entire unit. So 2.7 liters of fluorine gas. You don't need to write the word of, but you need to write the actual chemical name. Okay. Next question was, how many cubic decimeters would a 1.50 mole sample of xenon occupy at STP? So given 1.50 moles of xenon at STP, 1 is the volume. So we're going from moles to volume again, so it should be one step, but we have a problem. We want the answer in cubic decimeters, not liters. So first of all, let's just convert to liters first, okay? So 1.5 moles of xenon, use the 22.4 liters of xenon for every 1 mole conversion factor to get rid of the moles. You're left with just liters. And from here, You can convert liters to cubic centimeters.